Welcome to Lecture 25, 4.3, Logarithmic Functions. Alright, so first objective, convert between logarithmic and exponential functions. Alright, by definition, a logarithmic function, if x and b are positive real numbers such that b is not equal to 1, then y equals, and we say log base b of x, is called the logarithmic function with base b. Once again, for reading this, we say log base b of x, where y equals log base b of x is equivalent to b to the y power equals x. Okay, so this is where logs and exponents are sort of related to one another. Okay, so how are they related? Well, the base of the exponent and the base of the log are the same, but the exponent is what we would consider the answer for the log. And the answer for the exponent is what we would consider, this right here is called the argument of the log. Once again, the thing in green is the argument. All right, so for example 1, determine what the base and the argument of the following logarithms are. Go ahead, give the first one a try by yourself and see if you can determine it. All right, so the base is going to be 5. And I'll just go ahead and shorthand the argument. Argument is going to be 25. Now, for the next one, for b, this is a special case. You might say, well, look, you didn't write anything down there. This is what we would call the common log. Kind of like, you know, when we use a square root, we don't always write the 2. Well, for logs, log base 10 appears so often that mathematicians decided, you know what, we're not going to write in the 10 anymore. So if you see a log that does not have the 10 written in, you're allowed to assume it's base 10. So in this case, we have a base of 10, and our argument for this one is 100. Let me go ahead and highlight those. Now, for the next one, for c, this looks weird. It's ln. You might say, hey, this is the typo. No, it's not. This is actually called the natural log. All right, and this is where the number e comes into play. You remember the number e? Well, log base e also appears rather often, almost as much as log base 10, or about the same. But because we already used the shorthand of log for base 10, they said, you know what, we'll call ln natural log. And I use a scripted L. Some people use a capital L. I'll go ahead and let you decide which version you want to use. But those are the two different ways we can write this. So the question is, what's the base? Well, the base is e, which remember is about 2.72. And the argument is 78. So base e, technically ln, and, oops, wrong color. And the argument is 78. All right, so switching between logarithms and exponents. To switch between logarithms and exponents, we have the following rule. Y equals log base b of x is the same thing as b to the y power equals x, which we kind of saw previously. So we're going to go ahead and switch from logarithmic to exponential form. And what I like to do, if we have the log on the left-hand side, I use some arrows. The base to the answer, and we'll skip back over, is 16. So this is saying 2 raised to the 4th power is equal to 16. And I have just switched from logarithmic to exponential form. Okay, go ahead. Let's see. Ooh, for b, what's the base of the log? We don't see anything there, so we're allowed to assume it's a 10, remember? We'll go ahead and switch it again. 10 to the 2nd power is 100. Once again, we're just rewriting the logarithms into exponential form. Go ahead and try the next two by yourself and check in with me in a second. All right, so this is 7 to the 0 power is 1. And the next one, ooh, well, let me rewrite this real quick. That's log base e of e to the 3rd power. And sorry, this should have an answer that should equal 3. Okay, so equal to 3. Well, we can rewrite this. E to the third power equals 3. All right, that's a sort of a sneaky one. Now, example 3, write each exponential equation in logarithmic form. So this time we're going backwards. Well, remember for the rule, log base b of x equals y is equivalent to b to the y power equals x. So whatever is the exponent will be our answer, whatever's the answer there will be our argument, and the base will always stay the base. That's the easiest to remember. The base will always be the base. So we'll rewriting this. The base in our equation here is that. The answer is the 4. The 18 is going to be, oops, I switched the color here, sorry. That's the base, and the 18 is the answer. So rewriting this in log form, we have 4 equals log base 3 of 81. All right, go ahead and try to write the other one in exponential form. Well, what's the base? The base is 10, exponent is 2, answer is 100. So we have 100, oops, wait a second. We have log base 10 of 100 equals 2. All right, so switching between logs and exponents can be a little tricky, but a good skill to learn because it starts to come in handy for the next sections. 4.2, evaluate logarithmic expressions. Equivalence property of exponential expressions. So if b, x, and y are real numbers with b greater than 0 and b not equal to 1, then if we have b equals b and they're raised to some powers, this then implies that those two powers must be equal. So x must equals y. And this is only if the two bases are the exact same value. Okay, so how are we going to make use of this? Well, for example 4, to evaluate the following logarithmic expressions, I'm going to set this first one equal to y, because I don't know what the answer is, right? And then I'll go ahead and switch this to exponential notation. So 5 to the y power equals 25. We've switched into exponential form. So this is 5y equals 25. Now it doesn't look quite like what we have up here. We need to write the bases to be the same. Well, I know I can rewrite 25 as 5 squared. So now, because the bases are the same, I'm allowed to assume that the exponents are also the same, which means y equals 2. Okay, so sneaky way of bringing in algebra. Go ahead and try that for part B by yourself and check in with me in a second. All right, so for part B, we'll go ahead and set this to y once again. Let's go ahead and switch to exponential form. Then we have 3 to the y power equals 27. The bases aren't the same yet, so we're going to change 27 to base 3. So that looks to be about 3 to the third power. We just changed 27 to 3 to the third power. Oh, the bases are now the same. So we can go ahead and equate the exponents. Y must equal 3. Now the next one. Once again, we'll set it to a variable for solving. Let's go ahead and translate it into exponential form. 1/3 to the y power equals 9. Ooh, this one's a little less straightforward. Huh. How can I make these look the same? Well, I know I can rewrite 9 as 3 squared. How can I rewrite 1/3 into 3? Hey, that's a fraction. We can use the rule for exponents. We'll take the fraction and take the negative. So this will be 3 to the negative y power. Go ahead and equate the exponents because they're the same. Because we have the bases are the same. So remember, you need to have the bases the same to equate the exponents. Then we have negative y equals 2. We haven't solved for y yet, so let's go ahead and multiply both sides by negative 1. And we get y equals negative 2. We're doing pretty good. Now the next ones. I don't see any base for the log, so I'll go ahead and rewrite this with the base of 10. Remember, because if it doesn't have a base, that means it's base 10. We'll set this equal to y, and we'll go ahead and rewrite into exponential form. So once again, we're introducing the variable to make the solving simpler. There are ways to solve without introducing a variable, but often it's simpler to just introduce a variable. So now we want to find a way to change these guys to the same base. And I know I can rewrite 10,000 as 10 to some power. So let's go ahead and do that. 10,000 is going to be 10 to what power? 10 to the 4th power. All right, ooh, so the bases are now the same. Awesome. Remember, that's our goal, is to make the bases the same. Why? So you can equate the exponents. That's the reason we want the bases to be the same. Okay, equating the exponents, and we're good. The variable solved for, so y equals 4. Next one, log, I'll go ahead and write that base 10, 0.001 equals, and we'll throw in that variable for solving. Once again, let's change this to exponential form. 10 to the y power equals 0.0001. I want to try and make these look like the same base, but right now, they really don't. You know what? I can rewrite that decimal as something over a few tens, right? That'll be 1 over 10,000. The number of decimal places we have will be the number of zeros. Ooh, which I know is the same as 1 over 10 to the 4th power. These guys are almost the same. Let's go ahead and use that same fish out of water rule to get rid of the fraction and replace it with a negative. That'll be 10 to the y power equals 10 to the negative 4. Ooh, we're running out of room. Let's see. We'll go ahead and sneak over here. Hopefully the natural log doesn't take up too much room. Setting the exponents to the same, we get y equals negative 4. And there we go. Actually, you know what? I'll go ahead and just, since we don't have that much to do, I'll write it right below. Y equals negative 4. Okay. Now let's take a look at the last one. Ooh, natural log. Once again, we know that that is going to be log base e of e to the 7 equals, and we'll write that y for solving. Once again, introducing the variable. Change to exponential form, e to the y equals e to the 7. Oh, that was easy. The bases are already the same. So, y equals 7. And that's it. We're done. So introducing the variable and then changing from logarithmic to exponential really helps with simplifying. Now, let's estimate the following values without a calculator. Well, what would this be? Let's see. Setting this equal to y, we're trying to figure out 2 to what power gives me 15. Well, I don't know what powers that would be. I know that 2 to the, let's say 2 to the 3rd power is going to be 8, and then 2 to the 4th power is 16. So that must mean that 2 to the y power is somewhere in between these values, which means that y is somewhere between 3 and 4. So we'll say y is between 3 and 4, which then means log base 2 of 15 is between 3 and 4. We don't know which one it is exactly, but we're just estimating. Let's do the same for the next one. This, remember, is the log base 10. We'll go ahead and set that equal to y. And then change to exponential. So this is saying 10 to what power equals 45,680. Once again, we'll find a lower bound and an upper bound and compare. Well, let's see. That's 45,000. So I know that 10 to the 4th power is 10,000. Well, the next option would be 10 to the 5th power, which is 100,000. So that means that 10 to the y power is somewhere between those two. which then means that y is in between 4 and 5. So our answer would be the log of 45680 is between 4 and 5, period. Now we're going to take a look at some properties of logarithms. Once again, very important. So for log base b of 1, this is going to equal 0. Why? Well, if you changed it to exponential form, we're saying b to the 0 power equals 1, which we know is true for exponents. Let me go ahead and write that in blue because that's just the example. This is sort of where the rules come from. The next one, log base b of b. What is that going to equal? Well, that's going to equal 1. Once again, coming from the concept of b to the 1 is the same as itself. Next, we have b, log base b of b to the x power. Well, that is going to end up equaling x. This stems from the exponent rule of b to the x equals b to the x. Lastly, we have b raised to log base b of x. What does that equal? Well, that is also going to end up equaling x. So these two, the last two, are very similar, at least in the way you answer. And why is this? Well, this is because log base b of x is the same thing as log base b of x. So one thing to note, with logarithms and exponents, you need to be really careful about what items are your base, your log, and exponents, because you have a lot of variables floating around, so just keep in mind which one should be the exponents and so on. So some examples. Well, if we had log base 7 of 1, that's just going to equal 0. Whenever your argument is 1, your answer is always going to be 0. Next, an example. Log base 6 of 6 would be 1. These guys are matching. Then log base 10 of 10 to the x power. Notice I make sure to keep my base down below, kind of with the tail of the g. The log and the 10 are on the same, and then the exponent is above. So make sure to keep that sort of leveling when you're working with your answers. That is something that I'll kind of be checking for when grading. So make sure that you have these guys set up well in their correct, you could say, planes. This is going to equal x. And then lastly, an example, 5, log base 5 of 2. Well, that's just going to end up equaling 2. A way some people like to think of it is that the logs cancel each other out. Okay, we're going to go ahead and simplify the following. Try to simplify these by yourself and check back in with me in a second. Well, for a, notice the base and the argument are the same, so in a sense they cancel out, and we'll be left with the exponent of 14, which in our case is going to be 1. Sneaky, huh? All right, next one. I'll rewrite this so you can see that the bases are the same. So once again, you can sort of say they cancel, and we're left with 10. The next one. Notice the base of the log is the same as the base. We'll go ahead and say that those cancel. And there we go. Next one. Aha! The argument is 1, which means our answer is going to be 0. Next one. Looks like the bases are the same, so we can go ahead and, in a sense, cancel them, and we'll be left with 10. Next. Notice that's a natural log. This will be e times log base e of 6. So the logs sort of cancel, and we're left with 6. Next. That looks complicated. What is the base of that log? That's going to be 10. We'll go ahead and let those cancel, and then we're left with x squared plus y. All right, so always good to notice those cancelings because it makes your problem so much simpler. And now we're going to go ahead and graph the following functions using a table of values. So once again, do not use transformations. We would use transformations in Math 135, which is not Math 103. So for a table of values, It's easier a lot of times to graph if you went ahead and you switched this to exponential functions. So that would be 3 to the y equals x. All right, so let's go ahead and pick some values. As usual, I like to use -2, -1, 0, 1, and 2. Those are just my go-to values. But notice here, I would try to be solving these in a different way. I'd be trying to solve that, which I don't really know how to solve. So this time, I'm actually going to be picking the y values and solving for x. So I'm going to rewrite my table of values to be able to pick the y's and solve for x. But I'll still pick the same values for y because they still work. All right, so now we're solving here. 3 to the -2 power equals x. Well, 3 to the -2 is going to end up being 1 over 3 squared, which is 1 over 9. So this is going to be 1, 9, -2 as 1 point. Next, we'll have 3 to what power? -1. Solving that, we get 1 over 3. Then we'll have 3 to the 0, which comes out to 1. Then 3 to the 1 power, 3. And lastly, 3 to the 2nd power, which comes out to 9. Voila. There we go. I'll go ahead and write these out as coordinate sets. And then let's go ahead and graph these. Okay, so the first value, we have -1/9 1/9 -2, which is about there. Then we have 1/3 -1, about there, totally approximate because it's sort of hard to fit those on here. Then we have 1, 0. And 3, 1. And then 9, 2. Notice this looks a lot different than the exponents. It starts to head off in that direction. And one thing, pretty much for the generic logarithms, you're always going to have a vertical asymptote at x equals 0. All right, so go ahead and try graph the other one by yourself and check back in with me in a second. Once again, for graphing these, I like to try and switch it to exponential. Just makes things a little simpler for my brain. So half to the y power equals x. We'll go ahead and set up a table of values. As usual, I pick my generic values that I tend to like to use. They normally always work. And let's get started. So 1/2 to the -2 power. I'll go ahead and set these all up first. That'll be 1/2, 1/2, 1/2, and 1/2. And they're all being raised to, let's see, -1, 0, 1, and 2. And to be safe, I'll put these in parentheses so we know what the base is. So that's going to be taking the reciprocal of 1/2, which would be 4. Then 4 to the 2nd power would be, oh, sorry, no, 1/2. Let me write that out on the side so you see what's happening. So 1/2 to the -2, that would end up being 2 to the 2, which should be 4. So we have the point for -2. Next, once again, we'll take the reciprocal because of that negative. We'll be just left with 2 to -1. Anything to the 0 power is just 1. So we have 1, 0. That'll be 1/2. So we get 1/2, 1. And lastly, we have 1/4, which is 1/4, 2. I'll go ahead and graph these. Let's see what we get. So we have 4, -2. We have 2, -1. Then we have 1, 0. 1/2, 1. and then a fourth 2. Oh, notice this one is actually heading the opposite direction than the one we've graphed previously, which kind of makes sense because this one is a fraction and the other one was a whole number base. Once again, we're going to have our vertical asymptote at x equals 0 because we don't have any numbers being added or subtracted to our actual logarithm here. So our vertical asymptote is going to stay where it is. All right, make sure to remember your arrowheads and to label all of your points. All right, let's take a look at the next example. All right, example 8. Determine the domain of the following logarithmic functions. Graph the solution and answer in interval notation. Okay, so one of the main things about logarithms that we need to remember is that the argument needs to be greater than 0. So if we have a log base b of x, the x value must be greater than 0. All right, so we're going to keep that in mind. We have to make sure that anything that we put into our argument, it cannot make our argument negative. Just think about in life, arguments should always be productive and positive. Should never have a negative argument in life. Doesn't get you anywhere. So that's our goal. We want to see, all right, are there any x values that make this negative? And if so, we're going to take them out. So let's go ahead and solve this very similar to how we've been doing domain before. So solving for x, we'll subtract 4 from both sides. Then we get 2x greater than negative 4. Dividing by 2. And we get x is greater than negative 2. So let's go ahead and graph this. X needs to be greater than negative 2, but not equal to. And there we go. Then we'll go ahead and write domain of f of x. It's going to be from negative 2 to infinity. And those are the allowable values. If we picked any other values outside of the domain, let's pick a test point. Let's say I picked negative 10 and plugged that in. I would get 2 times negative 10 plus 4, which would be negative 20 plus 4, which would equal, negative 16. We can't have a negative argument, so that value would not work. All right, so it does look like we picked the right side. Okay, go ahead and see if you can try find the domain for part B. All right, so for part B, remember, we want to have the argument be positive, so we'll take that negative 10 times 2x, and we'll go ahead and see when it's greater than 0. Let's see, subtract 10 from both sides. Then we have negative 2x is greater than negative 10. Divide by a negative. And when I divide by negative, what happens? The sign switches. Mwaha. Alrighty, and then let's see, we get 5. So x is less than 5. We'll go ahead and graph this on a number line. X is less than 5, but not equal to. And go ahead and graph it there. So the domain for our function, g of x, remember to always put the domain name for the function, the function name. That will be negative infinity to 5, but not including 5. And lastly, let's take a look at this. Okay, we have 4x squared minus 9. And we want this to be greater than 0. Oh, but notice, this needs to be factored. It's quadratic. So go ahead and use the difference of squares to factor it. But once we do that, this should start to look familiar. We now have to factor, which means we have critical values, which then means that we need to use a table and pick test points. Oh dear, this one's looking like a bit more work than we thought. All right. Solving 2x equals 3, 2x equals negative 3. Almost solve for x. Divide by 2, divide by 2, divide by 2, divide by 2. So x is either 3 divided by 2 or x equals negative 3 over 2. These are my critical values. So we'll go ahead, set up our testing box for critical values. We have 2. We have negative 3 over 2, which would be negative 1.5. and positive 1.5. So I'll just go ahead and write that out as a reminder. This is 1.5 or negative 1.5. Okay, so setting up our test value box, we have our test point, then we have our factors, and what do we want them to end up equaling? We want them to be greater than 0. All right, so once again, where do we get the concept that we want them to be greater than 0? That comes from the actual equation. So pick a test point smaller than negative 1.5. I'll go ahead with negative 10, 0, and then 10. Remember, you pick the value from the interval. Plugging that in. So that's going to be plugging negative 10 into the 2x minus 3. We'll get a negative, and then plugging it into the next one, we'll also get a negative. So negative times negative will be positive. Ooh, and yes, that is greater than 0. So we'll go ahead and include that section in our answer. Now for the next section. Plugging in 0 to the 2x minus 3, we'll get a negative. And then plugging it into the 2x plus 3, we'll get a positive. But when we multiply the negative to the positive, we'll get a negative, which is not greater than 0, so we do not include that section in our answer. Next, we'll go ahead with the 10. Plugging that into 2x minus 3, we'll get a positive. And then with the 2x plus 3, we'll also get a positive. Multiplying those two positives together, we'll end up with a positive answer. Remember, we don't actually need to know what it is, we just need to know that it's positive. And yes, it is positive, so we'll include that section in our answer. Lastly, let's write our domain, the triumphant moment. The domain of k of x is negative infinity. Ooh, that was an ugly. Let me rewrite my infinity. Negative infinity to negative 1.5 union 1.5 to positive infinity. And that is our domain. So remember, if you have to end up factoring, you're going to need to do this chart for testing values. If you did not factor, you don't need to do the chart. All right, that is it for 4.3. Please email me if you have any questions.